Okay, we are very happy to have Ziquan Zhuang from Johns Hopkins University, and he will tell us about the local volume of KLT singularities and boundedness in general type MMP.
Okay, thank you, Carl. So thank you for having me here. It's my pleasure to speak in this seminar. So okay, so I'm going to talk about what's on the screen, local volumes of KLT singularities and boundedness in general type MMP. So I should start by saying that so most of the time I'm going to work over the field of characteristic zero. And if I ever forget to mention it, this most of this is joined with at least for this boundedness in general type MMP, this is joined with Jingjun Han and Lu Qi. Okay, so but maybe I should first start by telling you this invariant that I'm going to introduce and these objects that we are going to work with. So let me start with the notion of KLT singularity. So there's a type of singularity class that comes up naturally in birational geometry, especially if you run the minimal model program. So so throughout the talk, I'm going to use the following notation. So usually if I talk about singularities, I'll specify so X will be a variety, and then I'm going to choose the close point. Okay. But let me forget. Let me don't take the close point yet. Right. So I'm going to say a variety is KLT. Um, if first of all the canonical, so X will be a normal variety. Okay, so let me put that on as well. So we say X is KLT. If first of all the canonical divisor, which you can define on a normal variety, is Q cut here. And if you take a log resolution from Y to X, and this is one of the reasons I've worked with characteristic zero, but you can do this in general as well. So and for any prime divisor on Y, so usually we call this E a divisor over X. So I'll use this convention throughout the talk. So it's a prime divisor on some log resolution of X. Then I can define the so-called log discrepancy. Is defined as so 1 plus the order along E of the relative canonical divisor, right? So ky minus the pullback of kx. And we say x is KLT if this number is always positive for all E. Right? So roughly speaking, this means that if you look at holomorphic volume forms of X and you pull it back to Y, you will get better than poles. Okay, so the order is at least -1, bigger than -1. So that's roughly what this condition says. If you haven't seen this condition before, some examples to keep in mind are quotient singularities. Okay, so you start with maybe, for instance, the affine space, and you're modeled out by some finite subgroup of GLN, for instance. Another very important example would be the Korn over Fano variety. If let's keep it simple, let's say Korn over smooth Fano manifold. Okay. So Fano means the anti-canonical is ample. So these are some typical examples, and actually the general case is not very far from the second case. So if I relax the smoothness by KLT final condition and then allow deformations, that pretty much generates every KLT singularities. All right, so that's the basic definition, and And as I said, this comes up very naturally in the minimal model program. If you run the minimal model program starting with something that's smooth, you will end up with some singularity. And what you get on those singular varieties are exactly this class of KLT singularities, so to speak. Okay, so now that's the singularity part. Now what's this local volume? So as the name suggests, as the title suggests, this will be an invariant of KLT singularity, by which I mean um, a variety with KLT singularity together with some closed form, right? So as I said, that's my convention, that's my notation for a singularity. I'll call this a KLT singularity. Um, all right, so this was introduced by Shili maybe around 10 years ago. And there are several different ways to define it. So maybe the simplest way to define this is as follows. I'll write down the formula and then I'll explain a little bit. So the local volume of this KLT singularity, and the notation is volume hat, is going to be defined as the following infimum, where I run through all n primary ideals, where well, mx is the maximum ideal for the closed point, right? So inside the local ring, of course. And so for all such n primary ideals, we can take its the classical Hilbert-Samuel multiplicity, and then multiply that by the nth power of the log canonical threshold of this ideal, where n is the dimension of my variety, and this LCT stands for log canonical threshold. And what is this? So so the formal definition is the largest number, let's say t bigger than 0, such that when I put x comma when I consider this tth power of the ideal on my variety x, this pair is so-called log canonical. But this is really so this is of course a formal definition. What it really means is so here I define what is KLT by saying the log discrepancy is bigger than 0. If you replace that by bigger than or equal to 0, that gives you log canonical. So that's the definition of log canonical, and you can extend that to ideals basically, right? So pretty much this condition says that so for any prime divisor over x, I can also look at 1 plus the order of vanishing of ky minus the pullback of kx plus this fractional ideal, right? So if you take a high enough resolution, then the pullback of the ideal is also a divisor. So I can compute this order of vanishing, or you can also do this on x itself. Anyways, and I want this to be bigger than or equal to 0. So that's the definition. You take the largest number such that this holds. Okay, so intuitively, basically, you want polymorphic forms with a certain pole, so to speak, along this ideal. And when you pull it back, you want the singularities you get to be at least like poles. Okay, so that's one way to understand this. All right, so that's the log canonical threshold, and that's how you get the local volume. All right, so far this is just a definition. Nothing is really happening here. So what's really surprising is that this simple kind of looking formula actually has a lot of connections to other type of geometric conditions or other types of invariants. So let me give you some examples of such connection. So maybe the first one is really an example to begin with. So maybe I should first tell you what this number looks like in at least some example. Um, right, so now let's take the origin of an affine space. So that's probably the simplest singularity you can come up with. It's even smooth, or any smooth point, basically. And what's the local volume of a smooth point? Well, so actually, before Chili's definition, so maybe I should also mention before I talk about this example that so what I'm writing down above, so this is not the original definition. So this is really, so the invariant was introduced by Chili, but this was an equivalent definition given by Yichen Liu. Okay, so and later on I'll comment on the original definition. But I think this one is maybe simpler to write down. Okay, so now let's come back to the example of smooth point. So so actually the right-hand side that appear in this definition, so before taking the infimum, this kind of normalized multiplicity has been has played a role in the what's called birational rigidity. So this was a theorem proven by I think by Corti in dimension 2, and then by Defanay, Ein, and Mustafa. That in this situation, so um, so if X is a smooth point, then this LCT sub the n primary ideal to the nth power, so this times the multiplicity, this is always at least n to the n, okay, where n is dimension as before. And if you plug in and if you take A to be the maximum ideal, then equality is achieved. So then in this case, the log canonical threshold is exactly n, and the multiplicity is 1. Okay, so in particular, you get equality. But there are other ways to get equality as well. For instance, you can take the powers of the maximum ideal. All right, so basically, they proved this by toric degeneration. So you can imagine a smooth point is not so different from the origin of the affine space, which is a toric variety. So what they show is that in order to compute the smallest normalized multiplicity of this kind, you can always degenerate the ideal to some monomial ideal. And for monomial ideals, there's an explicit combinatorial formula for that. And if you take the minimum of that combinatorial formula, you will get this number. So this was proved by toric degeneration. To monomial ideals. And then you can imagine that by the same argument, you can try to compute. Okay, so then this implies that in our language, right? So the local volume of a smooth point of dimension n is exactly n to the n. Okay? Because yeah, so just by definition. So so now, as you can imagine, you can use the same toric degeneration argument to compute this number for basically every toric singularity. So then so Harold Bloom did this in one of his papers. So he give a recipe for computing the local volume of toric singularities in terms of a combinatorial formula, but maybe I won't write it down explicitly here, but you can imagine it's it, it's somewhat explicit. Okay, so that's the first example, and already in this example, knowing the local volume of a smooth point has some application already, and so I'm not going to elaborate on what goes in this direction, but for instance, there's already so at least a small variant of this already gives you the following statement. This was one of the main results in birational rigidity, which was proven by Amaso. So maybe at the time they didn't quite use this method, but afterwards people realized that you can actually do this using this invariant as well. So what can be shown using this local volume, for instance, is that if you take a smooth final hypersurface of top degree, so every smooth final hypersurface, let's say of degree n+1 in Pn+1. So I just want to use n for the dimension all the time. So this is so-called birationally super rigid. And in particular, this means that they are not rational. They are not birational to Pn. In fact, not birational to any smooth final variety except itself. Okay, so and as you can imagine, if you know the local volume for not just the smooth point, but also for other singularities, you can actually relax these smoothness assumptions to get irrationality result for other hypersurface of this degree. But let me don't go too much into that today. So that's one very interesting connection of this invariant, of course. Now the second application of this, or maybe connection of this invariant, maybe has more to do with the original motivation for introducing it. And so let me first remark that Shirley was a differential geometer. So the second result has some differential geometric flavor. So let me write down the theorem first. And this was proven by, I think, in increasing generality in several works by some combinations of Yu-Chen Liu and Cheyang Xu. So the result says the following. Um, let me tell you a special case first. So the special case is that, so earlier I said, if I take the cone over a smooth final manifold, then this is an example of a KLT singularity, and you can ask, what's its local volume? So so the theorem says that if so first of all, if this smooth final manifold V has a K-Einstein metric, then the local volume of this cone vertex, okay, so let me call X the vertex of my cone construction, then this local volume is exactly the anti-canonical volume of this final manifold V. Okay, so the top self-intersection of minus K, the anti-canonical. And in fact, that's almost an if and only if. So there is a so-called Yaotian-Donaldson conjecture that says that the existence of a Kähler-Einstein metric on a final variety is equivalent to an algebraic condition called K polystability. I'm not going to really define this here. It's just some algebraic condition that that exist. It's somewhat technical to write down here. So maybe the general statement of the theorem says that in general, so in the same context that X is the cone over some final variety, um, the local volume of this vertex is equal to the anti-canonical volume of the final variety, if and only if this final variety is so-called K-semi-stable. And since I didn't define this terms for you, I'm not going to elaborate too much. But at least as the name suggests, being K-semi-stable is not very far from polystable. Okay, so in some sense, a final variety is K-semi-stable if and only if it's a small deformation of some K-Einstein final variety. So that's one somewhat mysterious connection of this local volume invariant, which I define using commutative algebraic invariant with this differential geometric notion of K-Einstein metric. And where do this come from? So let me try to remark a little bit on the background. So roughly the reason is that so in Chile's original definition, he defined the local volume using a different formula, which is the following. It's also an infimum, but this time it runs over the valuations over the function field. Of the function field of x that's centered at this close point. All right, so maybe I should say so for valuations, I'm using the additive convention, right? So valuation means that if I multiply two element, then the value add up. And if I take the sum of A and B, then the value should be at least the minimum of A and B, of the value of A and value of B. Okay, so all right, so for any such valuations, you can also define what is log discrepancy. So this is not so relevant in this talk, so I'm not going to define this. And so that's going to be the replacement for log canonical threshold in this context. And there is also a replacement for the multiplicity term, which is called the volume of that valuation. So in some sense, the second term is so take the valuation ideals of this valuation, and you compute the asymptotic growth of its multiplicity. So that's this volume. All right, so that's the original definition. And in this context, you should really think of a valuation. I'm going to put this in quotes here because this is very vague. I'm not going to make this precise today. As some sort of non-Archimedean version of a metric. So so in Chile's definition, he was motivated by the question, right? So if you think about Archimedean metric, so that's the usual Riemannian or Kähler metric. You can talk about this Kähler-Einstein metric, so which are metrics with constant Ricci curvature. So in Shirley's original definition, there is vaguely the question of finding which valuation is the most Kähler-Einstein, so to speak. Okay, so in fact, so let me put this in a very vague sentence. So actually, sometimes starting with some Kähler metrics with some nice conditions, you can produce a valuation. And so in his original question, you start with some k-line star metric, and you want to find out which valuation do you get according to this more differential geometric construction, right? So basically, you get from a metric, you can look at some of this asymptotic behavior near the singularity, and this asymptotic behavior is captured by a valuation. So when defining this local volume, Shirley wants to find out which valuation is most likely to come from a k-line star metric. Now, in differential geometry, you can find k-line star metrics by minimizing certain energy functions among the space of all k-line metrics. So in this setup, so this local volume, this infimum above, you should think of this as some non-Archimedean version of this variational method, which is the one I described for finding k-line star metrics in differential geometry. So I believe that was part of Shirley's original motivation, and he finds that basically this serves that purpose. Now, coming back to the previous theorem that I told you, if you start with the cone over a k-line star found of variety, it's probably not so hard to imagine where the k-line star metric come from. So then, in some sense, the valuation that you can get, which is closest to the one that comes from this k-line star metric, is the exceptional divisor of the vertex blow-up. And so if you plug in the exceptional divisor of the vertex blow-up into this original formula, or alternatively, if you plug in the maximal ideal in the previous formula using normalized multiplicity, you will get this anti-canonical volume. So that's where it comes from. Okay, so that's another example I want to tell you. And so still on this list of connections, the third one I would like to mention is a connection to an invariant that people use a lot in commutative algebra, which is called F signature. So now let's temporarily work over field of characteristic P for this part. And so if I start with some singularity in characteristics P, then there's a Frobenius section. Let me call F the Frobenius. Then so the F signature is defined by, right, so first of all, I can take the Frobenius push forward, or maybe I can push forward the structure sheaf by some power of the Frobenius, so the eth power of the Frobenius, and I can decompose this this push forward into a free part and a non-free part. So so maybe I call so there's a free part of rank, let's call it A sub E, plus another part that has no free summon. Okay, so then the F signature of the singularity is defined as the limit of this A sub E divided by P to the E times the dimension as E goes to infinity. Okay, so as before, N is the dimension of this talk. So now if I start with the singularity in over field of characteristic 0, and it's KLT, I can take its reduction not P for large enough P, so I have to maybe spread it out a little bit over some finally generated Z algebra, and then you can do the reduction not P. So let me call the reduction XP. it's known that this reduction is strongly F regular for large enough P, which means that the F signature is going to be positive in this context. And then there's a conjecture, um, which is still largely open, but in a lot of examples, this is true. So the conjecture is that so when you take this reduction mod P and let P goes to infinity, I can look at the F signature, of course, but I can also take the limit as P goes to infinity. And so the weaker version of the conjecture says that this limit is always positive if the original x is KLT. The stronger version would say that this limit is at least bounded from below by some positive multiple of this normalized volume, where the coefficient in the front, so this C, is some positive constant that only depends on the dimension, which is n. So that explains the notation. So as I said, it's still a conjecture, but it's both. It's in a lot of examples it's true. So for instance, in the toric examples, you can verify this. And also for quotient singularities, this is not so hard, I believe. Yeah, but other than that, I think it's still largely open. I think a lot of people believe this. Okay, so now that I have give you some examples and applications of this local volume, I want to focus on what I would like to highlight today. So today, so I'm not going to expand on these applications anymore. I would like to tell you a more recent application of this local volume. And this is the second part of the title, which is boundedness in general type MMP. So this is a somewhat surprising application of this local volume because as you'll see shortly, the statement I'm going to write down does not even involve this local volume at all. But maybe before I get into that, I will double check. Are there any questions about the previous part? Before I move on to something that's a little bit different. Okay, if not, then let's continue. Okay, so earlier I said this KLT singularity comes very naturally in the minimal model program, which you recall MMP for convenience. So what does it do? So the MMP, it's in some sense a program. So it starts with some variety with mild singularity. That's a projective variety. With KLT singularity, for instance. So of course you can start with something smooth, but as you run this minimum model program, you end up with KLT singularity anyway. So let's just start from there. And so the steps in this NMP are the following. So at each step, you are going to contract curves um, with negative intersection number with the canonical divisor. Right? So at the end of the day, you want to make the canonical divisor as positive as possible. So everything you see, every time you see something negative, you contract it. So then this will lead to two possibilities. Either you get a divisorial contraction, or what's called a flip. Okay, so if you contract a divisor, that's the divisorial contraction. Sometimes you contract something of codimension at least two, and then you have to do something else to fix the variety to make sense of this intersection numbers afterwards. So that's called a flip. So technical details doesn't matter so much here. And then and then you go back on. Okay, if you see something that's contractible, you do it again. So and so repeat this several times, and the goal of this minimal model program at the end of the day is to produce a minimal model, which means the canonical divisor is left, so it has non-negative self-intersection, non-negative intersection with every curve. Okay, so if you see something that's contractible, you contract it. If not, then you get a minimal model. But of course, the question, the big open question, in the study of in this study, is that whether this program is actually going to terminate. And so that's the main conjecture. So conjecturally, every minimal model should terminate after finally many steps. But this is still largely open. So there are some progress in low dimensions, but in higher dimension, maybe the biggest result is due to so you recall BCHM, Burkhardt, Ashini, Haken, McKernan. So they say that if you start with a varieties of general type, so if X is projective ALT variety of general type, so being general type means that the canonical divisor is big. Okay, so in other words, it's it's Q-linear equivalent to the sum of an ample divisor plus an effective divisor. Okay, so this is ample, this is effective. All right, so if you have a varieties of general type, then we don't know if every MMP terminates in this case, but at least some MMP will terminate. So if you run on the MMP, the so-called MMP with scaling, terminates. So you don't really need to know what's MMP with scaling today. Basically, that means so at each step, so of the MMP, you are supposed to contract curves with negative intersection with the canonical divisor. But there are many such curves. So if you choose your curve carefully at each step, then you can arrange this step so that at the end of the day you will terminate with the minimal model. But if you don't choose your curve carefully, then we don't know. So that's what their theorem says. Now coming back to this termination conjecture in general, so there do exist some general approach to termination of the minimal model program based on some other conjectures. So let me try to tell you some of these known approaches. Oh, I see a question in the chat. Oh, so some statement about, okay, maybe I'll answer that at the end because I'm already over that part. Okay, so right, so now let me come back here first. Right, so I want to first tell you some known approaches to termination. So one of this approach was proposed by Shawcroft. So this approach is based on okay, so maybe I should first say, so this approach is based on another invariant of KLT singularity called minimal log discrepancy. And pretty much we have already seen this invariant, I just haven't wrote it down. So what's the minimal log discrepancy? I'll abbreviate this as MLD. So earlier we have seen this log discrepancy. Okay, so which is so if you start with a prime divisor over your variety, you have the log discrepancy, which is 1 plus the order of vanishing of the relative canonical divisor. Right, so pi is a log resolution. Use a prime divisor here. And so the minimal log discrepancy is defined as the smallest number that you see in this form, that you see as you vary these prime divisors. Okay, so I have to choose a base point x, and then this defined as so there's really a minimum of prime divisors whose image is x. Sorry, I take the log discrepancy, the smallest log discrepancy of prime divisors whose image is x. So that's the definition. And it's always positive if x is KLT. Right, so because all log discrepancy is positive. Now, so now look what does Shortgraph say? So he showed that if, so roughly speaking, if this minimal log discrepancy invariant satisfies two nice properties, if MLD satisfies lower semi-continuity and the ascending trend condition, I'll write this down shortly, then every MMP terminates. So that's the one version. A more precise version is the following statement. So suppose you start with your variety X and you start to run its minimum model program in some way. Okay, so each step is some kind of divisorial contraction of flip. Okay, so you continue. So there's some MMP. Where each step is your divisorial contraction or flips. Right, so then if the following condition shows, first of all, on each of these varieties that show up in the MMP, I can look at this minimal log discrepancy function. So if for all I, this function that takes a close point on xi to the minimal log discrepancy at this point is lower. This function is lower semi-continuous. And second, if I consider any of these varieties that show up in the MMP and any close point on them, and I compute the corresponding minimal log discrepancy, then and I put all these possible values together into a set. If I also know that this set satisfies the ascending trend condition, so that's the ACC part. Okay, so in other words, if you have an increasing sequence of numbers from this set of possible MLDs, this sequence is going to stabilize after finally many times. Okay, so if both conditions hold, then this particular MMP will terminate after finally many steps. Okay, so that's the precise version. So so the first theorem that we prove this was joined with Jingjun, Han, Lu Qi, and myself says that so if you start with the varieties of zero type, then the second condition hold. Um, and actually it's a little bit stronger than that. Then so we take the following set. So let me write it down. So consider all possible outputs, intermediate outputs of the MMP. So this will be a sequence of steps of some MMP starting from X. And for any close point on Y, the conclusion is that this set is actually finite. Okay, so in particular, if you start with a sequence of MMP starting from X, then you can take Y to be any of these Xi's, and so put together this set. It's a finite set, so of course it satisfies the descending train condition because there are only finitely many numbers you can choose from. So, um, so that's our first result. Let me call this theorem A. So in particular, this means that an easy corollary is that so at least if X is of general type, then okay, so let me put it this way. So if you know this minimal log discrepancy function is lower semi-continuous, then that would imply that every general type MMP is going to terminate. Okay, unfortunately, we don't know this yet, so that implication is still not so clear. But at least um, we reduce the number of conditions that one has to check. So that's the first theorem, and that has to do with this first approach for termination. There's another approach for proving termination, and this has to do with the boundedness of varieties that show up in this sequence of MMP. And actually this was the approach taken up in BCHN. So first of all, we can prove a slightly more general result than what's used in BCHN. So this in the same paper. So here's the statement. So suppose you have a sequence of MMP. Okay. At the beginning, we don't know whether this sequence will terminate or not. But let's assume that the set of all these varieties Xi belongs to a bounded family. Which means okay, so there are several ways to define this. One way to think about this is that they can be parameterized. Um, what to say? So so they can be parameterized. Okay, let me put it this way. They only show up in finitely many components of the Hilbert scheme. Okay, so there is this Hilbert scheme that parameterizes subvarieties of projective space. And it has infinitely many components, countably infinitely many. So if for some reason you can show that you only need finitely many components of the Hilbert scheme to enumerate varieties that show up in this entire sequence of the MMP, then this MMP must terminate. In some sense, that's an if and only if, of course, because if the MMP terminates after finitely many steps, then there are only finitely many varieties that show up in the sequence. So of course, it's a bounded family. But in particular, so in particular, this means that if you start running the MMP to get some intermediate outcome, maybe at some point you get to xi, then so basically none of the xi can be isomorphic to x, right? Because if you run the MMP and at some stage you get to a variety that's isomorphic to x, I can repeat the same sequence from there again, then I will get an infinite sequence of MMP that does not terminate at all. So that's one particular thing that has to be ruled out in order to prove this statement. But maybe I won't go into the details of this proof for the sake of time. But at least this suggests that so that's another approach. So maybe one way you can think about this boundedness approach is that so if you compare this with the previous one by Shawcroft, so if you just use the minimal log discrepancy, then we need to know two things, right? So we need to know it's some sort of finiteness, basically, this ascending train condition, and some further property, which is this lower semi-continuity. So the difference here is that so proving boundedness of the varieties that show up in the whole sequence is a little bit like saying that not just the minimal log discrepancy satisfies some finiteness condition, but actually every invariant that you can imagine is going to take value in some finite set throughout the whole MMP. So what this means is that if you can't show some extra properties of the invariant that you come up with, but you can show this this finiteness condition for not just one invariant, but for a lot of invariants, then your MMP is going to terminate. So that's the rough difference. Okay, so and if you don't know which invariant to choose from the beginning, then you just bound the variety itself. All right, so now unfortunately we can't really prove this is bounded if you start with the general type MMP. But we can show something that's a little bit weaker, and it's an interesting question whether this weaker condition is enough to get the termination. But that's the theorem B that I'm going to tell you. So as I said, we can't really show the varieties are bounded, but we can show that at least at each step of the MMP, in some sense, the part that you contract and the part that you glue back, those are bounded. Okay, so in some sense, at each step, the difference of the varieties are bounded. So let me try to write this down more carefully. So again, let's start with the projective varieties of general type. As before. Then the fibers of all so-called extremal contractions and the fibers of all flips in all possible MMP that starts from X. Okay, so let me just write KX MMP. Okay, because we are trying to make KX positive in the end. So all these fibers belong to a bounded family. So these fibers are the locus where you modify during this MMP process. Okay, so in other words, I consider the following set. Okay, so So yeah, so by the way, I need to explain to you what is an extremal contraction. So as I said, when you run the MMP, you do the following, right? So maybe you already have some initial steps already. You get to some intermediate model Y. So this will be a sequence of steps of some MMP already. So take anything like that. Now, starting from Y, if it's not a minimal model, then you are supposed to contract some kx negative curves. So I call that contraction extremal contraction. So contract k negative curves. Okay, so this is called the extremal contraction. So sometimes that's just the entire, so that's all you have to do for this step of the MMP. And sometimes it's not enough if this is a contraction whose exceptional occurs as codimension at least 2, so-called small contraction. In that case, you have to also take the flip. If the previous one is a small contraction. Okay, so let me call this F and the other one G. So then for any point in Z, I can look at the fiber of this contraction maps. Okay. So the claim is that when you make all possible choices in this construction, put together this whole set together, this is bounded. Okay, so all these fibers can be parameterized by finitely many components of the Hilbert field. So that's what the theorem says in a more precise way. All right, so that's the main statement. And as I said, so this does not really give you the boundedness of the whole variety, but I don't know, at least I don't know whether this can be used to show termination in the end, but we'll see. Right, so that's the statement. Before I try to tell you some ingredients about the proofs, are there any questions at this point?
So were you planning on giving a 60-minute talk, or
So I'll try to maybe use maybe another let's say 10 minutes or so. Yeah, so I don't think I need to use the full 1 hour and a half, but
we usually took a break. I mean, if we were going to use the longer one.
oh, okay. Yeah, sure. Okay. Yeah,
So
yeah,
so so
sounds good.
so
Yeah, I
okay, so
think this is
what
also a good place to take a break.
so why don't we take a 5-minute break, and yeah, and we'll pick up in 5 minutes. Oh,
Yeah.
actually, yeah, maybe you could answer Alex's
Maybe I
question.
can answer the questions from the chat now.
Yeah, exactly. All right.
Okay, so let me see. So the first question is
Oh,
so
so sorry. We'll resume at 35. So in 4 minutes from now. But yeah, okay. But you can answer chat questions if you want.
right, so the first question uh right, so let me just put it here very quickly. So so maybe the precise statement is the following. So so earlier I said if I take the cone over a smooth funnel, that's KLT. You can replace smooth by KLT, of course, because you already understand what's KLT in lower dimension. And usually, depending on convention, you can take the cone over a variety with some ample polarization, which is a line bundle. But you can also take a cone using some ample weight divisor. So that's an orbifold cone. So this is still KLT. And so the general statement is that so being KLT is equivalent to Q-Gorenstein deformation of such things. Okay, so for any KLT singularity, you can actually write down what's called the test configuration, which is an isotrivial degeneration that takes the original singularity and degenerate it to one of one of these guys. Okay, so that's one way to think about this. It's not particularly useful in the proofs, but it's more conceptual. And the second question, the dimension of the bounded families. Yeah, no, we don't know. So we only know it's bounded. But yeah, we don't have a very effective control of the dimensions. In general, yeah. It's like in general, it's really hard to compute the dimension of the Hilbert scheme sometimes. So yeah, and we can't do any better than that at least. Yeah, so at least I don't know. Yeah, sure. Yeah. Okay, so now let's come back and continue. So now maybe I'll just focus on theorem A to give you some idea of what kind of ingredient goes into the proof. The second theorem is more complicated, and a bit more technical. So um, so basically, I want to tell you how the local volume shows up in the proof, because so far we haven't seen them yet in this part of the applications. So so actually so this local volume, because of its connection to complex differential geometry, has been studied a lot in the case stability context. And so actually we have already found that so actually it has a lot of structures. So and some of this will be very useful in what I'm going to tell you next. So let me now let's come back to this local volume again. Uh, right. So earlier I told you some properties of this local volume. Um, but what's discovered in recent years are so there are two major properties that has been discovered in more recent years. So so the first one says that the first one usually goes under the name of stable degeneration. And this was originally conjectured by Shi Li and Chen Shi, but it's now proved as a theorem by combining the works of Harold Bloom, I think Shi Li, Xiaowei Wang, Chen Shi, myself. So I'm not going to give you the full statement. But here's the summary. It says that every KLT singularity has a local volume preserving isotrivial degeneration. So in fact, by a test configuration, if you know what that means. If not, just don't worry about it. So pretty much a little bit like the reverse process of what I wrote down earlier. To degeneration to a so-called K-polystable final cone singularity. So we don't need to know the meaning of every word here. So so a K-polystable final cone singularity is an algebraic condition, but it's equivalent to the existence of a Ricci flat Kähler cone metric. If you want to know what that's about, um, but pretty much so so earlier I said every KLT singularity can be obtained by some deformation of an orbifold cone, but actually can realize it as deformation of some very nice cone singularity. and moreover, is one important part. This degeneration is unique. So this polystable object is uniquely determined by the original KLT singularity. So that's one general result. And the other is a boundedness statement for this polystable final cone singularity. Let me call it some sort of local boundedness. This was worked out by Chunyang and myself. It says that if you fix the dimension and some positive lower bound on the local volume, so let me choose some positive number, then the set of K polystable final cone singularity with local volume at least this big, this set is also bounded. In a strong sense, meaning that you can actually write down a flat family of final cone singularities that enumerates all these K polystable final cone singularities without missing any. Okay, so maybe combining these two, the general philosophy so roughly the stable degeneration plus this local boundedness implies that in some sense this local volume so in some sense every KLT singularity, so if you want to know something about your KLT singularity, you just have to know what's the local volume. So this local volume is going to control most other invariants of your KLT singularity. Up to some finite ambiguity. Okay, so what do I mean over here? So right, so if you go back to what these two says, so once you know what's the local volume, then according to the local boundedness, there is only a bounded family of singularities of a polystable final cone singularities with that local volume. So it's just a fixed family. We don't know what that is explicitly, but it's some explicit family. And if you want to know a general KLT singularity with that local volume, you can always do this volume preserving stable degeneration to some final cone singularity, which already lives in this bounded family. So all you need to know, so all you want to know is contained in this process. Okay, so start with some bounded family where the invariants are most likely controlled, and you do a deformation. So if you can also control this invariant along that deformation, then you control the invariant that you want to study. So the actual theorem that we use to prove the first main result, this finiteness of the minimum log discrepancy, really boils down to the following two statements. Okay, so let me write it down as two theorems. The first one is what we prove in the same paper that says if you start with the projective KLT variety of general type, then there exists some epsilon positive such that for any sequence of MMP, so sequence of steps of your MMP, and any close point on Y, the local volume is at least this big. Okay, so it gets some control on the local volume through the MMP, the whole MMP process. And secondly, so this comes from my earlier drawing with the Chen that so if you fix some positive lower bound on the local volume and the dimension, then there exists a finite set S, depending only on this data, so the local volume and the dimension, such that for any KLT singularity with local volume at least this much, we have the minimum log discrepancy of this singularity belongs to this finite set. Okay, and of course, if you once you put these two together, that means if you start with a projective KLT varieties of general type and you run this any sequence of the MMP, then the minimal log discrepancy is going to belong to a finite set in any process that you come up with. You can come up with. So and so the second part is what I alluded to earlier, that that once you have some control on the local volume, then you will very likely get some control on other invariant. So depending on what type of invariant that you want to analyze, the argument would be somewhat different, but it's likely possible. Right. So maybe I won't expand so much on the proofs of this tool that much. There some part gets a bit technical. Let me just say very briefly. So so for the proof of this first one, so actually, the first one has something to do with the actual original motivation of this project. So actually, at the beginning of this project, what we really would like to study was the behavior of this local volume under the MMP. So so unfortunately, so ideally, it would be great if the local volume is non-decreasing in the MMP, and then you would get this lower bound automatically, because at the beginning, you have some varieties of KLT singularity, and it's known that for KLT singularity, the local volume is always positive. There was a general result proven by Chile. So if you know this local volume never decrease, then that's the ideal situation, and you get this automatically. But unfortunately, that's not the case. So so the workaround that we use is to introduce a global variant of volume, some sort of global normalized volume. So so at least if I restrict to this context, I can tell you what this global version looks like. So so there's an invariant called the alpha invariant of projected variety together with a big line bundle. So here my canonical divisor is big. So so this is defined. It's a little bit like log canonical threshold, but in the global sense. So I'm taking the uh the supremum of t bigger than 0, such that for any divisor that's Q linearly equivalent, Q divisor that's Q linearly equivalent to the canonical divisor, effective divisor. When I put the coefficient t in the front, then I get a log canonical pair. Okay, so as I suggest that this is a global version of the log canonical threshold. And so what happens is the following. So so now if I look at the alpha invariant raised to the nth power multiplied by the volume of the canonical divisor, so this number is non-decreasing in the MMP. Okay? And it's also positive. And we can always compare the local volume with this. right? So the left-hand side is not non-decreasing in the MMP, but the right-hand side does. So if you're stuck with something that's non-negative, that's positive, then it stays positive throughout the whole process. So that's how we get this theorem, basically. And for the second part, so so pretty much you want to so there are several steps actually. So so the minimal luck discrepancy according to the definition is a rational number because well so when you pull back this canonical divisor, it's Q constant. So when you pull it back, you'll run into some some um, some denominator when you compute its pullback of the coefficient of the pullback along some divisor. And so in order to get this finite set, there are um, two parts. So first of all, you need to control the denominator of this minimal luck discrepancy using the local volume, and then you have to get an upper bound. So let me just say in words. So the denominator really comes from this uniqueness. So um, so um, so let me just write down one step here. So for this second part, um, so what's really coming in here is a finite degree formula that says if you have a quadrilateral cover of KLT singularities, then the volume is multiplicative by the degree. And so the volume of any singularities cannot be bigger than the volume of a smooth point. So so this tells you that if you have a KLT singularity, you cannot have a quadrilateral cover whose degree is very big. And in particular, um, you can construct quadrilateral covers if you have a non-Cartier weight divisor, and the degree of that cover is the index, is the Cartier index of that divisor, and that's basically the denominator. So here we are pretty much saying that the denominator is controlled by n to the n over the volume of the singularity. So that's the first part. And the other part is to get an upper bound. So you need to produce some divisor whose luck discrepancy is small enough. So then you go back to this bounded family first. So on the bounded family, you can always find some divisor with bounded luck discrepancy. So the difficulty is to show that those divisors can be deformed along this volume-preserving degeneration. So that on a general chaotic singularity with the same local volume, you can still produce an exceptional divisor with bounded luck discrepancy. So that's the difficult part, and it involves basically some analysis of some CDGs using the local volume in terms of the family and the local volume. But maybe I won't get into those because it's going to be a little bit technical. So maybe I'll just stop here, but I'm happy to answer more questions if you have.
All right. Nice. Thanks, Ishwan. Um,
Yeah,
are there
thank
uh,
you.
are there other questions that um Yes, I can ask one. Is there any hope even in low dimensions of any sort of similar results in CAR-P or something?
Uh, right. So for instance, actually, I don't know. So actually, I don't know. So but I think one interesting direction, for instance, is so as I put it here, right? So
Yeah.
so the key part, one of the key statement here is to have a lower bound on this local volume during the
Yeah.
MMP process.
Hmm.
And earlier I mentioned that this local volume is some analog of the F signature.
Yeah.
But characteristic 0. So of course you can ask if you start with the varieties of general type and you start to run the MMP, whether the app signature stays bounded from below by some positive constant, which seems likely based on this result. But yeah, but I'm not so sure. That's
Mm,
my answer. I mean the other results that appear here, like the stable degeneration, boundedness, that really uses a lot of results in over C or in characteristic 0. So so those might be a little bit hard to generalize in characteristic P, but I haven't thought very carefully about this. In low dimension, maybe it's still possible, but yeah.
okay. Okay. Are there any other questions? All right. If not, let's thank this one again.
Yeah, thank you.
Thank you.